how do you calculate Ksp from molar solubility? So this question is a bit tricky, that requires multiple steps, but once we get it down, it's actually not too complicated, okay? Alright, so if in order to first get Ksp, we need to first think of a random molecule. Okay, that's what we're gonna work with. Okay, for the formula, we have A, X, B, Y. Okay, so it has different subscripts, and this dissociates. Well, in terms of that, we have to use this line because it's not a complete dissociation. That's what the Ksp is for. We have XA plus, whoops, forgot to put lowercase, XA plus YB. Okay, that in a sense would be your formula you're working with. Okay, and it would have, like, you know, the charges. It would be plus because it's a cation and an anion. This right here would be an anion, would be the A minus. I mean, oops, not B. It would be Y minus and X minus, Y plus and X minus. So the way it balanced out is pretty much saying that these charges would balance out in total to make sure that we still have a net charge of 0 from the original thing we started with. So overall though, that is the formula we're working with. Now, the formula for Ksp is that because this is typically solid, we disregard the product because usually it's products over reactants. But to calculate Ksp, because the reactants, like, it's usually just a solid there, we don't factor that in. So we have, okay, so ignoring really the charge, well, can't really ignore the charge, but we're gonna have A, the Y plus, okay, times the B X plus. Okay, so that's just a charge, but you have to put it to the power of these coefficients. So it's going to be to the power of X and to the power of Y. Okay, so with that being said, we now have, in a sense, a breakdown. And the reason why we get to put it to the power of is because that's what the coefficient does. It's not a direct multiplication. You're increasing it by that power. Okay? So now, when they give you molar solubility, right, it's pretty much an amount of the AXBY that dissolved. Okay? So they're like, the molar solubility was 0.13 moles per liter. That's what they give you. Okay? So with that being said, right, if you wanted to figure out how much of the A and the B was produced, you would actually break it down accordingly. Okay, you would have AXBY, for example, and you will see here, to convert them, be 1 mole based on this formula up there of AXBY is equal to whatever that X is in front, X moles. In fact, I'll make this no, I'll keep it lower, but just don't lose, okay? It will equal X moles, that's a coefficient, right, of A Y plus. And the same thing, actually, it would be, so whatever you have, you multiply it by that coefficient, and that would be what you get. And then same thing, actually, if it was now for the B, it'd be the Y moles, the coefficient there of B X minus per 1 mole of AX BY. Why am I saying all this? Okay, it's because now if we used AX BY, in a sense, was C, because we just got like a value for it, right? So AX BY is equal to C, right? We can actually now use this, okay, these coefficients, to replace that to form a better direct Ksp. So now what we have, okay, is that the Ksp formula is that as we replace this number, this value with just C, right? You will see that it would be X times C, if that makes sense, and this would be Y times C instead of the A and B. So then the Ksp value for that solid or whatever it is, it'd be X times C, okay? With that, you know, we don't really have to put the charge there. We can put the charge there just to be able to make sure that you're understanding it. But for them, I'm going to leave the charge out. You just know that whatever the amount is, it's going to be times that coefficient there. But you cannot forget your power. So X times C to the power of X times Y times C to the power of Y. That would be what you would use to calculate your Ksp. What does this mean? It means that if you're given the question, like we said, it was 0.13 moles of whatever, and it broke down to 2 moles of A and 1 mole of B, you would have, we plugged it in, right? It'd be 2 times 0.13 to the power of 2 times 1 times 0.13 to the power of 1. And you would get 2 times 0.13 squared times 0.13, because that's all of this is here. Your Ksp value, made up one for this one, would actually be 0.0088. Okay? That, in a sense, this formula here really is how you calculate your Ksp from molar solubility, because your molar solubility really is that C. C is your molar solubility, the value they give you in terms of like moles per liter. Alright, so that would be, this equation would be how you solve it based on the equation I've given you here. So with that being said, let's see how we did. Exactly, we did convert it correctly. A times S is pretty much like what we did with the X times C. So then when you replace it accordingly, you have X times CX, Y times C, Y. And that is what you use to calculate molar solubility, and this is correct. So let's move on now to question number 9. We have